Pick up with then checkpoint 4. So kind of just finishing up, it says evaluate. We're going to evaluate these, so it's a lot like what we just did. Alright, so we're going to put equal to x, and then when we do our circle or Bay method, we have 9 to the x equals 9. Remember, this is really 9 to the first, so there's no exponent there, so 1, so x equals 1. So anytime this base is the same as what's in the parentheses, it's always going to equal 1. Because this is just saying some number to what power is going to be that same number, which is always going to be the first power. For letter B, again, we can put this equal to x. And then we're saying 8 to what power equals 1. So what is that exponent going to be? Anytime we raise something to a power, we're going to get to 1. 0. So remember, anything to the 0 power is equal to 1. So that would be x equals 0. So anytime we have as our answer, if you think of base answer exponent, our answer being 1, it's always equal to 0. Okay, because again, that's saying what to the 0 power, anything to the 0 power is 1. Also, we have checkpoint 5 here. These are going to lead us to some properties that we're going to write down. So again, we'll put equals x. And we'd be saying 7 to the x power equals 7 to the 8th. So notice we have that equal bases here. So we can cancel these out, and we will get x equals 8. So whenever we have the base of our log being the same of the base of an exponent, those just cancel out. And as we look at letter B, although there's a log in letter B, where is that log? It's in the exponent, right? So this is actually an exponential form right now. It just happens to have a log in that exponent. So if we can rewrite this as a log using our Bay method. So our base is 3. That's what's being raised to a power. Our exponent is log base 3 of 17. And we can say it's equal to x. So if you look at the left side of that equation versus the right side of that equation, they both have log base 3 on the left, log base 3 on the right. On the left side, we have an x inside the parentheses, and on the right side, we have a 17 inside the parentheses. So what does x have to equal, you think? 17, because again, if the left side equals the right side and everything else on the same is the same on the left as the right, this x has to be the same as what's inside the parentheses, so x equals 17. So another property is that if you have, again, anytime you have a base of a log and a base of an exponent be the same, it just cancels out. You're left with 17. So that's going to lead us to a couple properties here. I would just write down, these properties here. Okay? So these other ones are just similar with the other ones. So our first property, we have log base b of 1 equals 0. So anytime that number in parentheses is a 1, it's always equal to 0. And that's because, again, if we did that circle here, e to the 0 equals 1. Anything to the 0 power is always 1. Oh no. Our second property, if I have log base b of b equals 1, well, if I ever have the same base as what's in the parentheses, the answer is always equal to 1, because b to the first always equals b. And then we call 3 and 4 inverse properties because they really undo each other. So kind of like we just said, if I ever have the base of this log the same as the base of an exponent, it's going to cancel. You're left with just the exponent. That's because b to the x equals b to the x. Okay? So those bases cancel and you're left with just what the exponent was. Similarly with here, the base is b, the log base b is b also. They cancel, you're left with just x. Again, that was because we rewrote this as a log. Base answer exponent. Our exponent is log base b of x. Our base is b, and our answer is x. So this just shows that these are canceling out. Those are canceling out. Anytime the base is the same, cancel out. So you can kind of just use these properties right away and you don't have to do a lot of work. If you know those properties are true, you can just say it's equal to that exponent. Do we have this or do we need more time? All right, so next we're going to look at the domain of a log, okay? So if we think of something like f of x equals 2 to the x, okay? That is our exponential function. Our exponential function looks something like this, okay? So this doesn't have to be perfect, but you can make a quick sketch. Just write f of x equals 2 to the x. Remember the exponential function has an asymptote on the x-axis, so it's close to the x-axis but not touch it, and then it goes up. So if we're going to find our domain and range for this, our domain for our original is going from negative infinity to infinity. It's going to go left forever and right forever. Our range, though, what's the lowest? So what do we get close to as we go down for the y? What's the y getting close to? Right? It's getting close to 0, but it's not touching it because there's an asymptote here. So I'm going to put parenthesis with a 0. Again, the parenthesis means it's getting close to but never actually equaling it, and it's going to go up to infinity then. So remember, the inverse of a exponential is a log. Okay? So f inverse of x is a log. And it would be the log with a base of 2. That's the whole reason we're learning about logs, because they are inverses of the exponential. So without us even being able to graph the log, we should be able to find our domain and range for that. Because what did we know about domain and range for inverses? Right, the domain is going to become the range becomes the domain. So the domain of the f of x is going to be the range or the inverse. And the range for the original becomes our domain. So what's going to happen here is we're now actually going to have an asymptote at x equals 0. So we're going to have a vertical asymptote for the log. It's going to get really close to 0 but not touch it. And see how this grows really fast? It grows slow in the beginning, then fast at the end. The inverse, the log, is going to be the opposite. It's going to grow fast in the beginning and then really slow at the end. So the log graph looks something like this. And again, it's not touching x equals 0 now. You have a vertical asymptote. And again, kind of notice that symmetry about y equals x. So the red one was y equals 2 to the x. That was the original one. The blue is the inverse. All right, so if we look at checkpoint 7, it says find the domain of f of x equals log base 4 of x minus 5. So if we kind of just think about our parent graphs in general, if I see x minus 5 inside those parentheses, which way is that going to shift our graph? Yeah, so this would be shifted right 5. So there's two ways you can think about this domain. Remember, the domain for just any log base is always going to be greater than 0. That's what we just saw on that previous page. It has a vertical asymptote that gets close to 0 but not touching it, goes on forever. Now we just move that asymptote right 5. So guess what our domain for this one's going to be now? Instead of it being from 0 to infinity, it's going to be 5 to infinity, because we just moved everything over 5. If you don't like doing it that way, thinking of it as your parent graphs, the other way you can do it is you can set your number inside parentheses greater than or equal to 0. Sorry, greater than 0. Because again, normally we're starting at 0, not equaling it. So the other way is you could do whatever's inside parentheses greater than 0, and then you could add 5. The other way is saying x is greater than 5, which is giving us that same thing. So it's up to you on how you'd like to do it. Whatever makes more sense to you. And our last checkpoint for the day, I'll get to that in a second. But either way, this is going to be our answer. This is our answer for the domain. And our range would always be all real numbers. Alright, and then the last little thing is what we see the natural log. Okay, so a log function with a base of e is called the natural log. Okay, so the function log base e, remember e's that thing in PERT, e to the RT, is usually written as ln of x. Okay, you say ln of x for natural log. If you look on your calculator, there is a natural log button on your calculator. Right above, below the log, there's an ln, which is natural log. So if I were you, I'd probably write log base e of x is the same as ln of x. You'll see that. And really, there's no difference between that. It's just that your base is e. So therefore, your domain for ln of x is still just greater than or equal to 0. It's just greater than 0. So it's touching, we're getting really close to 0, but not touching it, and going to infinity. Okay, so just because it has a base of e doesn't mean it's any different than any of the other bases we've seen. It's still the same shape of the graph, it's just that e is your base. So if we're looking at this one might be a little bit easier to think about as, okay, we know that this number has to be greater than 0. So I'm just going to do 4 minus x is greater than 0. So if you're asked to find the domain, just put whatever's inside the parenthesis greater than 0, and then you can solve for x. Here you have some choices on how to solve it. Here I usually subtract 4, negative x is greater than negative 4, and then we would divide by negative 1. Remember, when we divide, we have to change our signs. So if x is less than 4 would be an appropriate answer. We do want to write it in inequality form. So we write the highest it has to be is 4. And so anything from negative infinity to 4, but not equal to 4, would be our domain for letter A.